Okay, now we're going to look at some more vertical shrinks of parent graphs. Here we have a transform graph f of x equals 3/4 x squared. Now notice 3/4 is still less than 1. Let's see how that looks for the graph. So we're going to change a now to, well, let's start a at equal to 1. If we make a equal to, well, we can't actually make it 3/4. Let's get close to 0.7. You can see that it still vertically shrinks, just not as much as if it's 0.5. Okay, we can go between 0.7 and 0.8. The point is, as long as it's less than in between 0 and 1, it's going to shrink those y values. Okay, we can do the same thing. Let's go make a equal to 1. We haven't done log yet. Let's do log. If we make the number in front of log less than 1, we can see those y values shrink by that much. So in that case, they're about a third of what they would be because it's 0.3. Let's do, I don't know, 2 to the x. Same thing. The y values go down as the x values stay the same. Let's do a negative one. So even if we, what was that one I was just looking at? X cubed. Okay. So what happens when you make a negative? Not only does it, in fact, it flips first and then the y values shrink. That's very difficult to see in one swoop. But you can kind of see what if a is 0.4 for 0.4x cubed, you can kind of see what happens if it's negative 0.4. You're basically just taking when a is 0.4 and then taking that graph and flipping it. So I guess you could do either order, wouldn't matter. I guess you could flip first and then shrink the y values, or shrink the y values first and then flip it. Anyway, it is still shrinking the y values on top of the flip. Here's the proof for what you're going to do with any parent function whenever there's an a value in front of it. In other words, f of x is equal to some scalar times that function. For example, 1/3 times x squared or whatever. Just flip the equation, right, and then flip these two right here. Commutative property. So p of x times a is equal to f of x. Whatever that number is, just take it. Take your p values, multiply them by that number to get your transform f of x y values. In other words, the y values of p of x are stretched. That should be shrunk, shouldn't it? Yes, that should be shrunk. I don't know why I put that. Okay, in other words, the y values of p of x are shrunk by a factor of a to reach the y values of f of x. And by the way, they're keeping the same x values, right? Here's what our normal p of x chart looks like, just very generic. Again, the x values are going to be the same, the y values are going to change. You're just going to take the y values and multiply them by a. Now in this particular case, you're just going to put the a out front because you don't know what those y values are. But normally, you get some number back, right? Like we looked at with the, let's go back here. When we did the 1/2x squared, we actually got numbers back. So sometimes it helps to see the concreteness of that. But in general, you're going to get the y values like this. Again, the x values are going to stay the same. And your generic chart for f of x equals a times p of x is going to look like this. It's going to be the same for vertical stretching as well, just as a heads up. Final note, when f of x is equal to a times p of x and the absolute value of a is between 0 and 1, then the parent graph p of x will vertically shrink to reach the transform graph of f of x while keeping the same x values. That's going to be it for vertical shrink. If you have any questions about it, let me know.